Late autumn, 11 o'clock at night. A basement light hums fluorescent and cold. A hairline crack runs the length of the slab, 3 feet, maybe 4, a fraction wider than it was last winter. $8 of liquid sitting on a hardware store shelf can close that crack from the inside. Not patch it, close it. Grow new stone where the gap was. The chemistry was first written down in 1825 and has been used by industrial flooring contractors quietly for over a century. The title of this video says, "Big Concrete does not want you to know." That framing is sharper than the truth, and what the truth replaces it with is stranger. There is no big concrete cabal. What there is, instead, is a quiet economic structure that erases good answers when they do not fit a profitable business model. The Romans had one version of this chemistry. A wall in Privernum, Italy, still holds it together after 22 centuries. The Massachusetts Institute of Technology proved how it works in 2023. And it sits right now on a hardware store shelf for the price of a sandwich. Part 1. The reaction that never finished. Concrete is not a rock. It is a chemical reaction caught in suspended animation. When Portland cement meets water, microscopic crystals of calcium silicate hydrate, CSH in cement chemistry shorthand, grow and lock sand and gravel into a solid mass. According to a principle established by Trevall Powers in the 1940s, this reaction can only complete fully when the water-to-cement ratio is above 0.42. Below that ratio, a fraction of the cement particles never react. They sit dormant, embedded in the matrix, chemically alive but locked away from the water they need. Nano-indentation studies by Van Dam and colleagues have measured the unhydrated cement content in dense pastes at around 30%. Meaning roughly a third of the original cement, even years after pouring, remains chemically idle. A 2023 review of rehydration studies published in the journal Materials found that in concrete with a water-to-binder ratio of 0.3, about 17 to 22% of the cement stayed unreacted. These dormant grains will rehydrate when the right conditions return. Surrounding them is another substance, one with a quieter story. Calcium hydroxide, mineral name Portlandite, common name free lime, forms naturally during the original hydration. Hardened cement paste is, by volume, roughly 15 to 25% calcium hydroxide. Penn State engineering literature places it at 20 to 25% for normal mixes. Free lime adds almost nothing to strength. It dissolves in water. It creates the microscopic capillaries that let water seep in, freeze, expand, and split the slab apart. Every cracked driveway, every dusting basement, every weeping foundation wall is, at the molecular level, the story of calcium hydroxide doing what calcium hydroxide does. The chemistry to turn that liability into an asset existed before the United States entered the First World War. Part 2. MIT, a wall in Privernum, and the 2,000-year question. In January 2023, Admir Masic, professor of civil and environmental engineering at MIT, published a paper in Science Advances examining a wall in the ancient Italian town of Privernum, conquered by Rome in the 4th century BCE. The wall is still standing. The concrete in it is still bonded. Masic and his team had been bothered for years by small white chunks embedded throughout Roman concrete, called lime clasts, which earlier scholars dismissed as evidence of sloppy mixing. The team's microscopic and X-ray analysis told a different story. Those clasts were not mistakes. They were reactive reserves. When microcracks form in Roman concrete and water reaches a lime clast, the lime dissolves, releases calcium ions into the water, and the calcium-saturated solution flows back into the crack and recrystallizes, sealing the crack from the inside. Masic's team reproduced the effect in the laboratory. Hot-mixed Roman-style concrete healed cracks up to 0.6 of a millimeter wide. Modern Portland concrete generally cannot heal cracks beyond 0.3 of a millimeter. In 2024, Masic returned to Pompeii to a house frozen mid-renovation when Vesuvius erupted in 79 CE. Standing in the half-finished room, he later told Scientific American, in his own words, that he felt like a worker from that exact year. The Romans were not running a research program, they were running a recipe. The recipe carried, inside its own ingredients, the means of its own repair. The Roman approach to permanence was not to build something that could not break, it was to build something that could repair itself when it broke. That distinction matters. Modern engineering, almost without realizing it, chose the opposite philosophy: design for replacement. Part 3. The Ming Wall and the Bowl of Sticky Rice, 445–6. About 1,500 miles east of Pompeii, and roughly 14 centuries later, masons of the Ming dynasty built city walls and the long mountain stretches of the Great Wall using a mortar that should not have worked. They cooked sticky rice into a porridge and mixed it with slaked lime. The result has held bricks together since around the year 1500. Bingjian Zheng, a chemist at Zhejiang University, led the team that figured out why. Using chemical analysis and scanning electron microscopy, Zheng's group showed that amylopectin, a branched starch molecule abundant in glutinous rice, acts as a growth inhibitor on calcium carbonate crystals. The mortar develops a denser, finer-grained microstructure than pure lime. It resists water. It absorbs earthquake shocks instead of shattering. A Ming-era tomb sealed with this mortar reportedly survived a direct hit from a modern bulldozer. Two civilizations, two recipes, the same underlying principle. A binder that does not merely set, but contains within itself the means to fill the cracks it will inevitably develop. The principle is older than any modern patent. It does not belong to anyone. That, as we will see, is part of why it is so hard to sell. Part 4. 1825, when the West caught up. In 1825, the German chemist Johann Nepomuk von Fuchs documented a procedure for producing what he called water glass, a clear, viscous solution of sodium silicate made by fusing sodium carbonate with silica sand. The compound was not new in nature, but Fuchs gave it a reliable production method. From that moment on, the silica chemistry that the Romans had drawn from volcanic ash became something a chemist could pour from a beaker. For most of the 19th century, water glass was used for fireproofing, for preserving eggs, and as an adhesive. The bridge to concrete chemistry came in the early 20th century. Rudolph J. Wigg, an associate engineer at the United States Bureau of Standards from 1910 onward, published a long series of technologic papers on the properties of Portland cement mortars and concretes. His work with co-author Ph. Bates on the absorption and permeability of concrete, and his later studies on the action of alkali water and seawater on cement, were the first systematic American documentation of how the porosity and capillary structure of concrete actually determine its lifespan. Then, in 1925, a Dutch engineer named Joosten patented a two-stage chemical grouting process. Pump sodium silicate into porous soil first. Then pump in a solution of calcium chloride. The two solutions meet underground and form a gel that locks loose sand and gravel into something approaching solid stone. The Joosten process was used to stabilize the soils beneath the Berlin Underground in the 1930s and remains a standard technique in soil stabilization handbooks today. By the 1940s, sodium silicate had quietly become the industry standard for densifying industrial concrete floors. Warehouse owners knew it, polished concrete contractors knew it. Homeowners did not. Part 5. What actually happens in the capillary? When sodium silicate solution is sprayed onto cured concrete, capillary action pulls it down into the pore network. Inside those pores, it meets the free calcium hydroxide left over from the original hydration. The reaction is straightforward. Sodium silicate plus calcium hydroxide plus water yields calcium silicate hydrate plus sodium hydroxide. Na2SiO3 plus Ca, open parenthesis OH, close parenthesis 2, in the presence of water, produces CSH, the same gel that gave the original concrete its strength in the first place. The sodium silicate is not introducing foreign material. It is feeding the same reaction that should have completed during the original cure and never did. The newly formed CSH grows in the capillary that calcium hydroxide once occupied. The freeze-thaw pathway closes. The dust-shedding surface binds. The crack, if it is narrow enough, fills from the inside outward. Industry measurements of surface hardness on densified concrete report Mohs hardness improvements in the range of 30 to 50% over untreated slabs. A 2022 multi-scale study published in Construction and Building Materials using a composite of nanosilica sol gel together with lithium silicate and sodium silicate reported a Mohs hardness increase of 260%. But that result belongs to the composite system, not to plain sodium silicate alone. The honest figure for the chemistry sold on a hardware store shelf is the 30 to 50 range. Significant, durable, not magical. This is chemistry that does not need permission. If a grandfather poured a basement floor in 1958, the unhydrated cement embedded in that slab is still there. It is still capable of reacting. The crack he never quite fixed is, at the molecular level, still waiting for the silica that never arrived. Part 6. Why the chemistry faded. A structural reading. The title of this video says, Big Concrete does not want you to know. Look closer, and the picture is less melodramatic and more interesting. Sodium silicate is sold openly. Foundation Armor, Concrete Sealers, USA, Surfcoat, Ghost Shield, and a dozen other industrial chemistry suppliers listed on Home Depot and on their own catalogs. The United States concrete restoration market reached roughly $4.25 billion in 2024, projected near $7.33 billion by 2034, according to expert market research. The global concrete restoration market sits at about $17 billion. These are not small markets. They are not hiding anything. The question is not whether sodium silicate is suppressed. It is not. The question is why a homeowner walking into a hardware store at noon on Saturday will see 32 polyurethane crack fillers on the shelf and no water glass. 5 structural reasons account for it, and none of them require a conspiracy. First, sodium silicate cannot be patented. The compound has been in the public domain since Fuchs documented it 200 years ago. No company can win 20 years of exclusive sales by being the one who invented it. No exclusivity, no corporate champion, no marketing budget. Second, the unit margins are low. Sodium silicate retails for roughly $6 to $12 per quart. A name-brand polyurethane crack filler tube sells for $20 to $30 and lasts 1 or 2 winters before it fails. The shelf math favors the tube. Third, the product creates no recurring revenue. When water glass closes a crack by growing new CSH inside the capillary, The homeowner does not return next year. The polyurethane tube, by design, does. From a business development perspective, sodium silicate is a product that erases its own customer base. Fourth, there is no brandable SKU. Water glass is water glass. A homeowner cannot become loyal to it the way they can to a colored, scented, branded sealant in a designed package. No brand identity, no shelf priority, no advertising spend. Fifth, the channel is wrong. Sodium silicate is a business-to-business product. The salesmen call on industrial flooring contractors, on polished concrete polishers, on warehouse facilities managers. They do not call on homeowners. The chemistry never had a consumer marketing apparatus and was never going to grow one. This is not a conspiracy. It is market drift. A solution that works permanently, cheaply, generically, and from a B2B sales channel is structurally incapable of competing for shelf space against a solution that works temporarily, expensively, exclusively, and from a B2C channel. The better chemistry loses on every axis except the only one that matters in a basement, whether the crack closes. A product that works forever is not a product. It is a problem. Part 7. The Protocol. The procedure that industrial flooring contractors have used for decades, adapted to a basement crack, takes about 20 minutes of active work and a weekend to complete. Materials: 1 quart of sodium silicate solution at roughly 38 to 40% concentration, available from pottery supply houses, online chemistry suppliers, and most concrete sealer retailers. Typical price $6 to $12. A cheap pump garden sprayer, around $15 at any hardware store. Distilled or filtered water for dilution. Optional, for the juiced-in second step, a small bag of calcium chloride sold as ice melt, roughly $6 to $10. Preparation: sweep and vacuum the crack until no dust remains. If the slab is bone dry, mist it lightly with plain water first. A thirsty slab will pull the silicate solution in faster than it has time to react with the calcium hydroxide it needs to find. First pass: dilute the sodium silicate at roughly 1 part to 4 parts water. Mist the crack and the surrounding 12 inches of slab until the concrete darkens but does not pool. Wait 15 minutes. Mist again. Repeat until the surface stops absorbing, usually 2 to 3 passes. Wipe any white residue off the surrounding concrete with a damp cloth before it dries. Sodium silicate leaves cosmetic deposits if it is left to dry on the visible slab. The juiced-in step, for cracks slightly wider than a hairline. Wait 3 days for the first treatment to react and cure. Then mix 1 cup of calcium chloride into a gallon of clean water and mist the same area once. Wait 24 hours. Rinse with plain water. The 2 solutions meet inside the capillary network and form an insoluble silicate gel, the same chemistry that stabilized the soil beneath the Berlin Underground in 1933. That is the entire procedure. The full materials cost is under $20. The chemistry is older than penicillin. Part 8. Honest limitations. 3 caveats. They matter, and any honest treatment of this chemistry has to name them. Sodium silicate does not bridge cracks wider than roughly 1/16 of an inch on its own. Wider cracks must be packed first with fine silica sand, which the silicate then binds into the matrix. Cracks wider than 1/4 inch, cracks that are actively growing, and cracks caused by structural shift or by rebar corrosion underneath the slab are not chemistry problems at all. They are foundation problems. The correct response is a structural engineer, not a quart bottle. Second, sodium silicate will not penetrate a slab that has already been sealed with a thick epoxy or polyurethane coating. the solution needs porous concrete to do its work. If the surface is glossy and beads water, the chemistry stays on top and dries to a film that peels off in a year. And the Steelman, because it matters. Epoxy crack injection. The professional systems from Sika, from Simpson Strong-Tie, from a handful of other specialists, does things sodium silicate cannot do. It bridges large structural cracks. It cures in hours rather than days. It tolerates ongoing movement in the slab. For a foundation wall with a quarter-inch crack that flexes seasonally, professional epoxy injection is the right answer, and it earns its higher price. Sodium silicate is the right answer for a different category of damage. Hairline cracks, dusting surfaces, weeping basement walls, and the slow capillary failures that polymer fillers cannot permanently close because polymer fillers were never designed to. The right tool for the right wound. Closing. Handoff. A wall in Privernum, Italy has stood for 22 centuries because the Romans built repair into the recipe. A Ming Dynasty tomb has shrugged off a bulldozer because a chemist in 1500 thought to add a bowl of cooked rice. Johann Nepomuk von Fuchs synthesized the first water glass in 1825, and the chemistry has been in the public domain ever since. Joosten patented the two-step in 1925. Wigg at the Bureau of Standards measured what porosity does to a slab 110 years ago. None of this is hidden. All of it sits in plain sight outside the shelves where homeowners are taught to look. The fluorescent basement light is still humming. The hairline crack is still there, 3 feet long, a fraction wider than last winter. $8 of liquid will reach the unhydrated cement that has been waiting since 1958 for the silica that never arrived. Tonight, the bottle. Tomorrow, the mist. Find the smallest crack in the house. Measure it tonight against the edge of a coin, a quarter, a dime, whichever is closer to hand. Photograph the coin against the crack with the date visible. Spray the solution as described above. Come back in 30 days, the same coin, the same crack, the same camera angle. Post both photographs below this video with the date and a single line of result. The industry will not fund a study to compare a 50-cent treatment to a $25 tube. 6,000 basements posted in a comment thread can answer that question in a month. The comments below become the field laboratory that no marketing budget will pay for. What was lost was not the chemistry, it was the habit of using it. The habit is one comment and one weekend away from returning.